Hey, welcome back, Marauders. This is video 4.6, Solution Stoichiometry. In this video, you're not really learning anything new. What you're doing is combining some things that you've already learned. So in chapter 4, we've been learning about solutions. We've been learning about the formula for molarity. Molarity is equal to moles per liter, moles of solute divided by liters of solution, and that's how we measure the concentration of a solution. And then back in chapter 3, we learned about stoichiometry. We did a lot of problems where you started with a certain number of grams of reactant and found out how many grams of product could be produced. So we're not really doing anything new today. We're just combining what we learned about molarity or concentration and what we know about stoichiometry. So our general stoichiometry problems, we started with grams of something. We used molar mass to go from grams to moles. And then we used the mole ratio in the balanced equation to go from moles of one thing to moles of another. And then we used molar mass to go back into grams at the end. We also know, or we've learned in chapter 4 about the formula for molarity. Molarity is equal to moles per liter. And so if we know the volume of a solution and we know its molarity, the volume times the molarity is going to give us the number of moles. So that's another way to get from what your starting information is, a volume and a molarity. You can get to number of moles. And then we can proceed like we've done in the past. Or maybe there'll be some questions that ask us to get a volume at the end. So we may start with grams of a reactant and then ask what volume of a product could be produced. So we'll take a look at a couple practice problems. Again, there's nothing really new here. It's just putting together things that we've been learning about, writing balanced equations, using stoichiometry, and using concentration or molarity. So this first example, what volume of 0.3 molar magnesium chloride is needed to precipitate all of the silver from 10 milliliters of 0.5 molar silver nitrate solution? All right, so we're mixing together two solutions. Let's start by writing an equation. So we have magnesium chloride, MgCl2, and silver nitrate, AgNO3. Okay, so your products are going to be magnesium nitrate, MgNO3 2, and silver chloride, AgCl. Okay, and we know that silver chloride is going to be the precipitate. That's going to be the solid that forms. All right, so we're going to look at what we're starting with. We're starting with 10 milliliters of 0.5 molar silver nitrate. So we have 10 milliliters of 0.5 molar AgNO3. All right, well, what does molarity mean? Molarity means moles per liter. So when you have 0.5 molar AgNO3, what that really means is that we have 0.5 moles of AgNO3 for every 1 liter of solution. So I think rather than, it's going to be given to you as molarity, but I think it's easier in the problem to write it out as moles per liter. All right. The volume of that solution was 10 milliliters. I'm going to change that to liters. So divide by 1,000.01 liters of that solution. We'll multiply these together. And if you multiply the volume times the molarity, you'll notice that liters cancel out, and now we have moles. All right, so once we have moles of AgNO3, we know that we want moles of AgNO3 down here on our next step. And I forgot to go balance the equations. So let's go back and do that. So we have 2 chlorines. So we need a 2 here, 2 silvers. You need a 2 there, 2 nitrates. So now we've got a balanced equation. And then what the question's asking us is about the amount of magnesium chloride. So we'll put moles of MgCl2 on the top. And then we'll look at the ratio between these things. So it's 1 magnesium chloride for every 2 silver nitrate. All right, and then our last step, it's saying, let's see, what volume of 0.3 molar magnesium chloride is needed. So 0.3 molar means 0.3 moles per liter. But if we look down here at our problem, we know we want moles of MgCl2 to be down here at the bottom so that it can cancel out. So what we're going to do is we're going to use the molarity, but we're going to invert it. We're going to put the 0.3 moles on the bottom and 1 liter on the top. Okay, so the molarity means moles per liter. But we can use that as a conversion factor, and we can flip it upside down so that the moles of magnesium chloride cancel out. It'll look like that. And now we can check our work, make sure everything's canceling out. The liters cancel with liters, moles of silver nitrate with moles of silver nitrate, moles of magnesium chloride with moles of magnesium chloride, and we'll get liters of the solution at the end. And I believe you get 0.0083 liters of that solution. Okay. So in this question, what we did was we started with the volume of a solution, and then we used the molarity formula to find out how many moles we had. We used the mole ratio in a balanced equation to go from moles of one thing to moles of another. And then rather than getting the final answer in grams, we came back up here and turned it back into a volume, since that's what the question was asking us. All right, a couple more practice problems. This one says, what mass of solid is formed when 150 milliliters of 0.5 molar magnesium chloride is mixed with 250 milliliters of 1 molar sodium hydroxide? All right, so probably good to start with a balanced equation. So we have our reactants magnesium chloride, MgCl2, plus sodium hydroxide, NaOH. And so your product's magnesium hydroxide, MgOH2, and sodium chloride, NaCl. All right, and so sodium chloride, that's very soluble. That's going to be your aqueous, so the sodium and the chloride are just spectators. And the magnesium hydroxide, that's going to be your solid. We should balance the equations. We have, let's see, 2 hydroxides here, so we'll put a 2 there. We have 2 chlorides, 2 sodiums, so we need a 2 here. And then the equation should be balanced. So in this problem, it tells us we have 150 milliliters of 0.5 molar magnesium chloride. We'll change that into liters right away, so that'll be 0.15 liters. And that's 0.5 mole per liter solution. And then we were also given 250 milliliters, so 0.25 liters of a 1 molar solution, so 1.0 moles per liter. All right, so this problem is a limiting reactant type problem. We're given the amounts of both reactants and asked how much of the product can be produced. So we know how much of this we have, how much of this we have. Not given in grams, but given in volume and molarity. And we're going to try to figure out how much of this product is produced. So it's limiting reactant. We're going to do 2 separate problems. We'll see which one makes less, and that will be the amount that can actually be produced, and it'll tell us which one the limiting reactant was. All right, so I'm doing volume times molarity, and again, I changed the molarity to look like moles per liter. So this was for the MgCl2. Okay, we had 150 milliliters of 0.5 molar magnesium chloride. So that's this step, changing it from volume into moles. And then the next step will be to use the ratio in the balanced equation. So in my balanced equation, I'm making 1 mole of MgOH2 for every 1 mole of MgCl2. And then this question asks us about what mass of the solid can form. So we know what the solid is, it's magnesium hydroxide. We'll use the molar mass of magnesium hydroxide, so I add that together. I think it's 58.3 grams of MgOH2 for every 1 mole of MgOH2. Okay. But we don't know if that's going to be our answer because this is a limiting reactant problem. We don't know which one's going to run out first, the magnesium chloride or the sodium hydroxide. So we'll do the same thing down here for the sodium hydroxide. All right, so from the problem, we had 250 milliliters or 0.25 liters, and it was a 1 molar solution. So 1 mole of sodium hydroxide for every liter of solution. The liters will cancel out. That'll give us moles of sodium hydroxide. So we know moles of sodium hydroxide should go the bottom of our next step. And we will have moles of magnesium hydroxide, the product we're interested in, on top. And the ratio between these, so 2 sodium hydroxides are needed to make 1 magnesium hydroxide. And then we'll use the molar mass, 58.3 grams MgOH2 for every 1 mole of MgOH2. Okay, so we'll do both of these on our calculators. We'll get 4.37 grams of magnesium hydroxide up here. And down here we get 7.28 grams of magnesium hydroxide. And so since 4.37 is less, that's how much can actually be produced. The magnesium chloride is your limiting reactant, and the sodium hydroxide is going to be our excess reactant. There's one other type of question that you're going to see in this section, and that's for titrations. So what are titrations? There's a couple different types, but the most common type is a neutralization reaction between an acid and a base. In this reaction, an indicator will be used. An indicator is a substance that changes color based on the pH of the solution. And it's going to be used to determine when a solution has reached the equivalence point. The equivalence point is when there are equal number of moles of hydrogen and hydroxide. So you have an acid which has hydrogen ions, a base which has hydroxide ions, and they cancel each other out, or they neutralize each other. And when there's equal number of moles of hydrogen and hydroxide have been added, then it's at the equivalence point, and you can use that to calculate the concentration of an unknown. So typically the setup in a titration is that you have a burette, which is a really accurate way of measuring the standard solution. So this one, you know the molarity and you know the volume of the standard solution up here. You know both the volume and the molarity, hopefully to a very precise measurement. And then down here we have an unknown solution. So this is your unknown molarity, but you do know the volume. So you know both the volume and the molarity of your standard solution. You know only the volume and not the molarity of the unknown, and that's the whole purpose, is to find out what's the molarity of your unknown.